today we are very happy to host Serdar Kadioglu from Brown University and also Group Vice President of AI at Fidelity Investments. So at Fidelity, he started collaborations with NVIDIA and Amazon, and previously he worked at Oracle and Adobe. His academic research is at the intersection of AI and discrete optimization, and his practical interests are in building high-impact products while contributing to open source systems. We are very happy to have you, Hocam. Stage is yours. Thank you very much for accepting our invitation.
Likewise, thank you very much. Hello and welcome, everyone. It's a great pleasure to be here. I think the last time I was here for a talk was almost 10 years ago, and things have changed drastically in the field. So very, very happy to be back. This New Year's Eve, my grandmother even talked about ChatGPT, and she asked me about my opinions. So I guess it's fair to assume that everybody is witnessing the remarkable improvements that is provided by LLMs these days. But what might not be very obvious or as obvious is what's their performance when considering very niche domains, one of which is optimization for the interest of this talk. And that's exactly what I'm going to talk about today. My name is Serdar. In my current role, I help Fidelity Investments to take AI theory in broad sense and infuse it into applications and products, whether they are external user-facing or internal associate-facing. And I'd like to present some of our recent work in envisioning a future as modeling assistants where we use LLMs as the main driver.
Hocam, before you start, do you accept questions during the talk or at the end?
Yeah, I'm happy to take clarifying questions and happy to take discussions at the end, which might be more interesting. So please feel to ask any clarification questions. I'm going to start maybe by saying a word on optimization and constraint technology. I'm going to use the terms interchangeably for this talk and would like to mention their great practical importance. They're very industrially relevant, whether you're talking about airline crew scheduling or freight transportation, supply chains, container shipments, job shop scheduling, product configuration, employee scheduling, resource allocation in the cloud. And I'm just using the examples that I had a chance to work on, hands-on on large-scale applications. And this is quite an established technology and enjoys a wide range of applications. And over the years, these optimization solvers and constraint solvers have enjoyed significant speed-ups, both provided by theoretical approaches and practical advances. At the same time, a lot of high-level models designed to make this technology available to many people. But what remained the same for decades is the overall process of how do we approach these problems, which essentially involves the de facto model and run strategy, which essentially looks like this. A user is responsible to look at the problem requirements, turn them into what we call a constraint model, and then a constraint solver or an optimization solver runs that model in order to find a solution. And when I say a user here, I'm not talking about an end user like my grandmother, absolutely not. Typically people with PhDs and have domain expertise in this topics. And for everybody else, this remains to be a barrier as of today. I'm gonna, mention, what a modeling is, but it might be a good opportunity to share with you this quote from Professor Eugene Freuder. Dates almost 30 years back in time in ACM 96, where he says, constraint programming or constraint technology represents one of the closed approaches in computer science towards the holy grail of programming, where the user states the problem and the computer solves it. And that's essentially what I'm calling modeling today. And we can look at specifically what that looks like on an example. And here, he lives in Boston, so here's me and Gene getting a coffee, and we're chatting about how that holy grail, how that evolved over the last decade. So before I dive further into talk, I just want to give an example of what I mean by the user states the problem and the computer solves it. And hopefully using that example, get a sense of what do I mean by constraint satisfaction problems or combinatorial optimization, and give a sense of declarative modeling approaches, okay? The example itself is not important, just I want to see the process of how this goes. I'm going to use maybe a hello world of this domain, a crypto arithmetic puzzle called Send More Money. And on the picture, you're seeing Ellen Newell, who is considered to be the first person to write an AI program in 1955. This is the logic theorem prover that was able to use heuristic programming and prove a couple dozen math theorems. And he's showing a Send More Money example on the whiteboard there, talking about symbolic processes and symbolic representations. About 20 years later, Newell and Simon received the ACM Turing Award in '75 for their contributions to AI. So I'm going to use this puzzle to solve the problem. The story that, at least the version I'm aware of, goes something like this. A student needs some pocket money and sends this puzzle to their parents, send more money, and now the parents are tasked with figuring out how much money to wire for their college kid. We take a problem like this. The requirements are essentially the desired properties, the business rules, the specifications. I'm going to gloss over those for this talk. This is super hard to gather in practice. You need to talk to people who understand a different domain. Not every information they give you is relevant, but assume that I have the requirements. So I'm going to gloss over that part. So let's assume that the requirements are there. Essentially, when I say a model, I'm not talking about a machine learning model or a language model. I'm talking about optimization models or constraint models, which essentially turns these requirements into analytical or semantic formulations. What that exactly looks like depends on the paradigm. So whether you're talking about, if you're familiar with operations research, you can think of this as linear programming or integer programming or mixed integer programming. If you're coming more from an AI and logic background, you can think about satisfiability solvers, sub modular theory, SMT solvers, or constraint programming solvers. So what exactly that looks like depends on the paradigm. But even within one paradigm, there might be multiple models to solve the problem. So not all models are equal. But what's common to all of these paradigms are that they are declarative. So we are not going to write imperative programs. What we're going to do is to specify the desired properties about what a solution is, not necessarily how to find it, as we would do in imperative programming. All right, so let's go on to modeling. How do we turn the requirements into formulations? And I'm going to give you the recipe of 3 ingredients that you need that works for any constraint model in the world, which is essentially variables. So these are the unknowns of your problem, and the domains, which are the possible values that these variables can take. And then you need constraints to link those variables together so that you can specify a desired property. And that essentially describes a CSV, a constraint satisfaction problem or a decision problem. And optionally, you can add an objective function that maybe takes a feasible solution and gives you an objective value. And then you have a combinatorial optimization problem. So let's see the requirements again for Send More Money. In this example, I have digits. Each character stands for a unique digit. The usual position notation applies. And if something is repeated like E, that is the same digit essentially. Okay, so these are requirements. I assume this is given. I told you what we need. We need decision variables, we need domains, we need constraints. In this case, the decision variables, the unknowns, are essentially the digits. So any of the unique digits here is my unknowns and my decision variable. What's their domains? They're digits, so it's from 0 to 9. But a careful I could immediately see that S and M cannot be 0, so they have to be 1. So you could do a bit of domain propagation, as you would call it, or filtering, and say that the domain for SMN is from 1 to 9, and for others it's 0 to 9. These are discrete integers. What are the constraints? We have essentially 2 constraints in this case. The linear arithmetic needs to hold, and also these are unique letters, so they need to be different numbers. So I have 2 types of constraints. How can we specify them? Well, this is the standard notation. So 1000 times S plus 100 times E and so on. So you could just write this down. So this is one way to put the linear equality constraint. I mentioned to you there might be multiple models. Another way to do summation, if you remember, back in primary math, you might use a carry variable. So you could also say D plus E equals Y, but maybe there's a carry, which I don't know if there is or not. So the domain of the carry variables now is 0 and 1. And then you can just write this going forward. N plus R plus maybe a C1 that I don't know if it exists equals E plus 10 times a carry C2, which I don't know whether it exists or not. And another careful, I would immediately see that because C4 has to be M, and that can't be 0, and C4's domain is 0 to 1, you know M is 1. So initially I said it's 1 to 9, but now I can see that it's actually M equals 1. So this is the type of filtering that these constraint solvers would do. And then the last thing you would need is a inequality. So none of these should be equal to each other. What you can do is you can do pairwise. So for every X and Y, you could say X is not equal to, so S is not equal to E is not equal to N is not equal to S, and so on. Or you could use something, what we call a global constraint, that actually captures this structure nicely, which is an all different constraint that takes an n-ary relationship. So n of these variables, and you say, I want them to have distinct values. And there's a beautiful filtering algorithm that uses graph theory underneath that would do the type of filtering we did with m being 1 or 0 and so on. So now that we have a model, what do you do next? Essentially, you would take this model and send it to a solver. And what are the solvers out there? There's many of them. So here's a few that I wanted to list here. So you would take this model and you would send them to one of these solvers. You might recognize some of the names. I have a typical test. Whenever I meet a Google employee who is not in the Google OR tools team, I ask them if they know about Google OR tools. I have not seen a person that says yes so far. When they say, I'll take that title off. But until then, it's the best kept secret otherwise. And I worked with the Oracle as a proprietary constraint solver, but if you use any one of them, they look and feel the same. They work differently under the hood, but essentially that's the process of, when I say a model, you take the requirements, you turn them into a constraint model, then you send a solver, and if you do that, you get back the solution. So I'm happy to take any clarification questions. I hope this process makes sense. The example is not important. Could have been any one of the industrial applications I mentioned. It could be the crew scheduling, it could be the logistics, it could be the cloud allocation, but it looks the same. You collect the requirements, turn them into constraint models, then utilize a solver to get a solution. Sounds good? Okay. So, yes, please.
Is it that Google employees do not need these solvers, or do they use something else like Grovio?
So not all of these solvers comes from the same paradigm. The CPLEX solver is an operations research solver. So if your problem is more like an optimization, this is what you might use. The CPU optimizer is more like if you have a semantic problem.
Hear about inside Google.
Well, I think, part of it, the reason is like it requires a bit of niche expertise to understand and be able to use these solvers. Like, if you didn't know that all different constraints existed, how would you even specify that constraint? And as a, thank you for that question. That's an excellent segue. So maybe we don't need PhDs to be able to use and benefit from this technology. Is there a future where you can think about a Holy Grail 2.0 with some modeling assistance that could help us? Right. So that is essentially the main part of the talk. Okay. Now that we have a sense of what modeling looks like, the question is, how do we approach the Holy Grail in the presence of large language models today? One could say, why don't I just send more money? The student needs this amount of cash, sends a message to their parents, give it to an LLM and ask the LLM the answer. Why do I have to do that? And I just did that, last night, actually. When I used Llama 3.2, completely couldn't solve it. GPT-4 is able to solve it, but it's not very clear to me how it does, because it could either be a repetition of, this is a very hello world example, so it could just be there. There's an optimization version of that problem, which is send most money, and it doesn't solve that one. So it's not very clear how it solves, and doesn't even solve a little variant of it either. So clearly there's some work in terms of reasoning that these models can provide us. But the good news is it's not like we don't know how to do the arithmetic. We know how to solve these problems. The bottleneck is how to model them. So if you didn't know all different, you wouldn't be able to model it nicely. So can we use LLMs? Not necessarily to find me the exact solution, but if I could get the model out of them, I have the solvers available and I can use them. So that's sort of the idea. And we put this into a position paper coined Holy Grail 2.0, where I'm taking, almost like mimicking the same process that I've showed you on the send more money example, where I have the natural language text, that's the problem description. I want to ask an LLM to model it. And once I have the model, I can still use one of the off-the-shelf solvers and get the solution out. Okay. We can now break this even further and say that, okay, a modeling is essentially, well, you need to first formulate it. So I did an abstract formulation, but then, there's a bunch of different solvers that understand this formulation. So now I need to translate it in an exact solver specification so I can, break this even further. So maybe I can do a formulation first and then a translation. And you can open this box even further and decompose these into necessary building blocks. I'll just give you one blueprint that seems reasonable to us at least, where we can talk about NER, which is the named entity recognition. So given a problem, what are the entities that's of interest to me? What's their relationship with each other? Maybe I can figure that out. And again, the formulation of an abstraction and then translating that into a specific instantiation of a code essentially that a solver understands. I like this type of decomposition because within each block, I can either use an LLM itself to do the block, but I can use, the best solution I could build for that case and study them separately and understand how they behave as opposed to just posting a question to an LLM and getting a black box answer. So that's sort of like, one of the motivations of why we're decomposing it this way. And if you go that route, you realize, maybe this is not just a one-time thing. You can now think about some conversational agents where, the user might see that the problem is unsatisfiable. Who guarantees that the solution would be? Maybe something was misspecified, or they need explanations, or they don't really know what constraint they need to do. So there's some constraint acquisition. So you can think of this as an interactive process where you can start with something, refine the model, run it, verify it. If it's unsatisfiable, you can look at the minimum unsatisfied subsets, and so on and so forth. So there's an entire domain of conversational constraint solving. And in fact, this has been quite a hot topic lately. There's a lot of work going on, not just in our group. Another position paper, a research manifesto on optimization copilot. So think of this as like the GitHub copilot, but specialized into optimization domain. And many others have studied this. People decided to use maybe different formats like LaTeX to solvers. So maybe we should write this in LaTeX format that's easier for LLMs to understand and whatnot. IBM is a modeling assistant that kind of does it in a way that is templatized. So they maybe take some templates and hold some guardrails around it. Interestingly, Microsoft is looking into this. They have LLMs for supply chain optimization. So they're not just doing generic optimization, but working on a specific problem. And one of my favorite ones is the Meet Mate, which is a even more specialized one that is an interactive decision support for a meeting schedule. So, maybe at one of the updates to Microsoft Outlook, we will see Meet Mate as one of the tools in the
chat, and it just figures out that it's time suitable for everyone.
Something like that.
That
I don't know exactly the product, but you can see where this is going. So, the topic is relevant, and it's kind of getting infused into practical applications as well.
So, like from a textual description, is there one formulation, or is there some uncertainty around it?
Right. So there is, as I mentioned, the formulation depends on the paradigm, and even within one paradigm, there can be multiple models. Not all models are equal. Some might be better than others. So yes, there might be multiple. And in fact, in our example, the linear constraint, I had almost two models, one with the carry variable and one without the carry variable.
But for example, violations are not tolerated, right? In linear programming, two variables should not be equal to each other kind of thing. And LLMs are not very good with these kind of enforcements, right?
Correct. So yes, these are, these are deterministic at the end of the day, and something is feasible or is not feasible, and something is optimal or is not optimal. So that's why, I think, Llama, when I say, okay, send more money, solve it, it's having a hard time solving it, but we know how to solve these problems to a certain extent. So if I can get a model out of the LLM, then I can still use my solver technology on top of that. So that's sort of like, how I'd like to approach it. Maybe, another fantastic question. So that's a good segue. Thank you again. Maybe this is time to give a little demo to make it a bit more concrete. I'm going to show two demos, in fact. One is the NER for opt, and the other is chat opt. So let's start with chat opt, assuming the internet holds. I need to stop the sharing and switch to my browser. Give me 1 second. It's all right. I just need to do this again once I wanted to go back. Okay, so let's see if the internet holds. So I'll start with the chat opt. This is the conversational agent that I was referring to you about. And I do have a, let's do the same problem that we looked at the slides. I'll use the send more money example, and I have it here. So I'm going to use it directly rather than typing it. So, here's a problem description given in natural text. I can send it to our agent. And what it is going to do is it's going to try to, the building blocks I showed you, it's trying to figure out the relationships between, what are the decision variables. The same manipulation we did on slide is trying to understand what are the unknowns, what are the constraints, how are they connected to each other. And at the end of the day, it's trying to come up with a solver specification. In this case, it's using CPMPy, it's a modeling language, but you can see that these are now decision variables, SNM. It figured out that they can't be zero already, which we did on the slide as well. And it used the all different rather than the binary inequalities. And it opted for the equality constraint without the carry variable. So, and then it's going to go and execute it, runs the code. In fact, if something funny happened, there's an error in the code. It noticed the compilation error because it used probably some API that doesn't exist. In this case, it says that instead of using int, I need to use that value. So it realized that, went back, updated the code, run it, and got a solver. So the family needs to send 10,650. Now I can ask a bit more. I can, interact with it and so on, which, I'm not gonna do live. Question?
Can we try the same send more money, but just change the letters?
Change the letters.
Like ABC.
You didn't memorize because it's a common
Because
example.
the example exists.
That's what I want.
Okay. Great suggestion. I'm not gonna go and try to do that. I'll do that immediately after the talk and let you know.
It's a live demo, hocam.
Yeah, I mean, I'm already happy that it worked. So, I'm not gonna.
It's impressive, very impressive.
But I should have mentioned, this is our collaboration with the UCL group in Belgium. So all the kudos goes to them for their work in building this. Other questions, comments on this? But you see, how this can go. This is the standard conversational interface, except that it's very, very specific to, in this case, CPMPy as the modeling language and an optimization and satisfaction.
Does it do this step-by-step reasoning thing? Is it why?
I'll tell a little bit more about what it does under the hood. So that's a great segue again. Thank you.
I'm here. We planned this last night.
Great host. All right, so this is chat opt. I want to go to something else now called NER for opt, which is I want to spend some time on this one as well. It's essentially very related, but instead of the whole modeling and solving, what I'm trying to do here is I want to study one of the building blocks in detail. So I'm going to give this a text. This is a free form text. What it does is it's going to try to recognize the named entities in this text. So in this case, for instance, it recognizes that the total is a constraint direction and 150K is a limit. And this cautious asset investment is useless. Like there's nothing interesting about it. This is not relevant to us. But money market fund is a variable, yields 2%, which is a parameter, and the objective is the return, and so on and so forth. So this is the NER for opt problem. Given text, we're trying to understand what are the relevant entities for optimization. And there's multiple ways to solve that, but at least, here's another, you can play around with this, give some text and see what it does and what it doesn't do. And there are multiple ways on how you could do that I want to talk a little bit about. Does this example make sense? So NER for opt is just one building block that tries to get these entities. Chat opt is a bit more full-fledged, that actually goes and not only identifies these, but eventually turns them into the exact solver instantiation, runs the solvers behind the scenes, comes back and is able to interact with you. Okay, so now that we have the demo out of the way, let me go back to the slides.
same mistake. Yes, the same place.
The what thing?
The like compilation error.
I'll give you the link. Just don't crash the server. Be a responsible user. I mean, clearly there is interest in using this, which is very nice to see. So let's maybe in this. So this is a good 30 minutes. Let's look at what's happening on the chat top to Fatma Hoja's question, and I'll talk on NER for opt as well. And at the end we can see where does this take us. And if I have time, I also want to step out of this presentation and say a little bit about our research at Fidelity Investments to give a sense of what's practically relevant to us these days. Okay, so what's under the hood? Essentially, this is sort of the blueprint for ChatOpt. So given the problem description, it's doing this NER that I showed you. From there, it goes to an abstract formulation like we did on the slides, then translate into the CPM-PI specification. So all of the prompts and everything is specialized for those cases. And if it recognizes an error, solves and refines, and it can accept user input. We use some in-context learning and chain of thought under the hood as well, but essentially it's a wrapper around an LLM system. But it doesn't have to be LLM. For NER, you could use something else, and I'm going to talk about NER for ops specific. Regarding in-context learning, what we can do is we can give, as part of our prompt, you just don't send the problem specification, but you can send some examples of, okay, here's another one and a constraint model for that. So just so that, it sees some positive examples of how to turn text into constraint models. You could do this randomly or, fix static examples, or try to, if it's a send more money, you try to maybe pick up a relevant or a similar crypto arithmetic puzzle. So you could do this example selection in a number of different ways. And you have to figure out how do you select one, how many of them you need to include, and so on and so forth. Here's one example. In this case, this is a problem description that's going to come in at the bottom, as you see there. And then we have one example in the context that shows how to go from a text to a model to steer the LLM response in a similar direction as the example given in context. We can make this a bit better if we actually add a bit of annotations. So given a bit of a reasoning, okay, that's a variable. This is why we need it. That is, basically connect with this abstraction, which is a bit too much to go maybe from text to an immediate symbolic abstraction to a bit more annotated examples. So if you do that, that seems to be quite helpful for LLM to get a sense of the translation in between. And I already showed you the example. This was a backup slide in case the live show didn't work, but it comes up with the CPM-PI. It understands that this is Python implementation and generates the code and executes it, and you can go back to it. I showed you one example, but maybe to generalize a bit more, I'm going to show results on two data sets. One's an optimization problem, one is logic puzzles. And how would you even evaluate, if you just look at it, like how do you even know these things are correct or not? You could say, okay, did it get the constraints right? So if there was 5 constraints, did it get the constraints right? Did it get the entire problem right? And the hardest one is, did it get the solution correctly? Like this is, if it gets the solution correctly, you have a bit more of a verification that at least a candidate to say that that's the case. Yeah.
It's not like just a translation task, right? You don't have task description and the task is to match it to some Python code. Have you tried this? This doesn't work, or like, do you have to intervene and use these name entity recognition relation, like this specific format? Does it need it? Because I mean, the bitter lesson is that if we interrupt it, it does things worse, right? Like it makes things worse. So maybe this formulating it like a translation from description to Python code, would it maybe work better?
Possibly, but again, this is now a bit speculation based on my experience how these things work. It comes down to like how well it understands the specific domain. So as opposed to general text generation or generic code generation, like in Python or Java, how much of the optimization translations these things are trained on and how good that is.
There's some mapping.
Like there's all sorts of domain expertise, understanding these solvers. So the abilities of these systems so it's not just coding in Python anymore, right? So yes, this is Python language at the end of the day, but there's something a bit more in this declarative language that is less well known, at least what we can observe in LLMs.
The format is so specific. It's almost like another language, right? To me, maybe it's not that different from English to German translation, right? Like
correct. And how much data you need to do that, right? How long you need for machine translation to work well. And that's definitely not the case for us here. So I think that's very, like, I think, you could just do the same, assuming you have the same data advantage, which we don't. It would be amazing. I'd love someone for doing that. So, if you introduce the in-context learning, you get some, nice improvements, whether you use a similar text or similar examples or using MMR, which is basically trying to get similar but diverse examples in it. It seems to be adding value. And here's some results with Mixtral. The solution accuracy is less than the constraint or the problem accuracy, so there's still some road to go. This could both mean, the models are not entirely correct, but also maybe they're not the best models, so the solvers are having a hard time to get to a solution, even though the abstract specification might be correct. And even though it's with the best model, these are NP-hard problems, so we might not even be able to solve it at the end of the day. So this is, I doubt it will go to 100% unless you're working with very simple processes. I mean, this was a very light introduction to what's under the hood. I have more details on the NER for opt side, if I want to maybe spend some time on that side. Maybe a bit more formal specification of what we're trying to do. So in this case, we are given a sequence of tokens. So, you can think of it as words and a string, the sentence S. And your goal is to basically to find tuples that denotes the start and end position where those specific tokens exist. So you have these tuples. And what are the tokens or the named entities that we are interested in? In our case, I'm interested in the variables, the constraint direction, the limit, objective name, direction, and the parameters. I already showed you the example on the Hugging Face demo. For instance, if you have 2 advertising channels, morning TV shows, and social media, the blues are the variables, so we want to pick that up. And if you have a constraint that says social media needs to be at least 30, you need to pick that at least as a constraint direction that's going to bound your limits, and so on and so on. So one could say, okay, why do we need this NER for opt specification? This is the standard named entity recognition, so you could just have used NER instead. It is, true that this is a bit syntactic, but if I compare NER, the classical NER, with what we're trying to achieve here, first of all, just the application is different. As in instead of question answering or information retrieval, we're trying to do this for optimization problems. But more importantly, NER is, in our case, the NER for opt works for multi-sentence word problems, and they have high level of composition among them, so things relate to each other, and they're very ambiguous as you read through this. Okay, so it's quite different from NER in that sense. An example that I always, find quite funny, and that exists in the data itself. If I talk about cities, for instance, Istanbul, Paris, Boston, they all share something. But when I say an objective as an entity, the number of trucks can be an objective. The number of coconuts can be an objective. They don't really share any semantics amount, or even though they are part of the same entity relationship. Plus, it can't be domain specific. So we want to be able to do this when you want to optimize the trucks and you want to optimize the coconuts. But the point is the objective variable, even though the domain could be very, very different. And going back to your comment about data, like it's difficult to find even training data, even for self-supervised learning in NLP settings. And here we have an extreme case where not just you need human labelers, but you need human labelers who understand these technologies, has a PhD in them, can write these models in the first place, in a good way, and so on and so forth. So extremely low data regime for us. So because of these reasons, I think it's an interesting problem to study. And I'm going to show you how we approach it. Essentially, it's a systematic way of understanding, okay, if I want to predict these entities, how would I do with a classical model? How would I do with some semantic approaches from modern NLP? Can I use some data augmentation, fine-tuning, and so on and so forth? So the approach is going to get complicated as we go along. But essentially, the components fall under three criteria: the features. How do we get the features? The feature extraction. Can we do feature engineering because we understand the domain? Can I learn the features? So this is all under the features umbrella. In terms of the models that operate on those features, we're going to use conditional random fields, CRF, which is very common for NER tasks, and neural networks, and some data augmentation and fine-tuning as a data-centric approach. Conditional random fields, this is a quick slide to give a sense. It's more like, almost like a logistic regression in a sequential prediction task discriminative model. The important bit is, you have these tokens XIs, and you have the feature extraction functions that looks at those tokens and gets a number of properties out of them. And what you're training for when you work with a CRF model is to understand the weights, how much you need to weight these different features extracted from the tokens. Okay, and I'll give you examples of what these feature extractions looks like, and you optimize that with the standard mini batch SGD and so on. So we take the input, we go to tokens, we extract features from those tokens, we have the CRF model on top, and we're trying to predict OBI tasks. And I should mention this is a supervised exercise, so I have some labeled data where I know the tags. So for instance, I want to maximize my profit. Your feature extraction functions could be, what are, is it a noun, or is it a verb, or is it a pronoun, and so on. And you might have multiple of those, right? So whether it's a numerical character, whether it's a hyphen inside, and whatnot. So these are like very standard, classical NLP, grammatical features, dependency parsing, part of speech tagging, and so on. So this all exists out of the shelf. Some morphology like word shape, whether they're capitalized or not. So you can generate those features. So these things exist. And at the end, you have the labels in the output. So the first one, I want to, there's nothing interesting there. And then they maximize the objective. You're trying to learn the weights that would correspond to your feature vectors. So you could do that. So that would give you the classical NLP out of the box. This is what you get. Okay, we do understand the optimization domain. So we can also do some feature engineering on top of that. The simplest is maximize and minimize are clear objective directions, and at least at most are clear constraint directions. So you could just sit down and, okay, I've done this before. Let me just come up with some vocabulary. Or you could go even a bit more, deeper. You could say that, well, conjuncting propositional chunks, for instance, commercials with famous actors, these things typically happens to be variables and so on. So you could try to understand your domain as much as you can and engineer some of the features that might be interesting, apart from what exists out of the box from the classical NLP. There are many others, but I'm just giving you a sense of what these might look like. And this is, even taking a step further, objective is you could actually sit down and write a regular automata that would match an objective variable. Here's one example. So if I take a sentence like profit to be maximized, this sentence is a member of this regular language. So it goes to the upper chain. Profit is a subject, and then the to be maximized the objective direction. And the second sentence is a bit more complicated. It follows one of the paths as well. But you could engineer this as good as, be my guest. You can write your own regular automata that would match an optimization variable. Okay. I'm just giving you a sense of like what you could engineer. There are some others. You could use multiple contexts. You can look at windows on the left and right and so on. Okay, so classical NLP, existing syntactic and morphological features, feature engineering on top because we understand the optimization domain. And maybe as a rival to that, how about feature learning? Why do we need to come up with these brittle, very static features? We can actually learn these things. And essentially the idea is to use some recurrent architectures. In this case, we use the bird style encoders. In our experiments, that's going to be Roberta. I can get the embeddings of the tokens. I know the labels. I can set up a fully connected layer, turn this into a token classification problem, and train my embeddings and learn features that correspond to them. Instead of using deterministic feature extractors, I can now use embeddings that are trained to predict these entities. And okay, so that also exists off the shelf. Now, what can we do on top? Well, these things are not trained. They are trained for generic tasks. What we could do is, find some domain-specific corpora, not as big as machine translation, but we can go out there and get some convex optimization books, game theory books, standard, course textbooks and whatnot, and do a standard mask language modeling. And at the time, this was the first, as far as we are aware, approach to fine-tune on the optimization corpora. So some time was spent on building this corpora itself, and now you can fine-tune this thing, and now you have a bit of an advantage on top of on top of existing embeddings.
Not just the feature learning part, you're also replacing the CRF, right? You're not doing CRF on top of deep learning features.
That is correct. So this is with the neural network, the fully connected neural network all the way. Okay. I'm going to show a hybrid on how to combine the two in a second. But yes, so the initial version was the CRF model with the feature extractors or our engineered features. This is the token classification with the embeddings with a fully connected layer on top to train with my labels, or fine-tuned on optimization corpora. And there's a bunch of things you could do with the data, but I'm going to skip them maybe in the interest of time. But this one is interesting. I want to give you a sense of why this is a very difficult problem. If I read the first sentence and the second sentence, a doctor wants to prescribe two types of medicine, diabetic pill and a diabetic shot. So these are clearly variables. Per dose, the diabetic pill delivers 1 unit of glucose and 2 units of blood pressure reducing medicine. Okay, so let's stop there. At that point, we're asking the LLM or any approach to figure out that blood pressure reducing medicine is the objective. If you're reading this yourself, you don't know that was the objective so far. So it's a very difficult task to actually, because what separates a variable from an objective variable is nothing. Just they are both variables, just one of them is a direction on top. So the ambiguity, the multi-sentence composition, and the ambiguity around it this is a very difficult. It's not like standard NER. I think that's a good example. Like by the second sentence, you need to figure out that. And if you keep reading it, it's not clear until you get to the very bottom. Maximize the amount of total pressure reducing medicine. That is, as a human, this is where I would realize that was it. Well, you could do some hacks. We could actually take some sentences from the bottom and append it to the top. The LLM doesn't need to read the text as we read it, so I can actually do some data augmentation and send it to the LLM in a different format. So, and all of these things do quite help. Okay, and I'll mention the hybrid model. So, what you could also do on top of that is to take the neural network prediction and add that as one more feature into your CRF, and let the CRF learn how to weight that in the existence of the other feature extractors. So that's the hybrid version.
The neural network, because these all happened in vision, right? Like 10 years ago when we were switching, we first changed the features, used CRF, then we started learning the CRF part.
Right.
First the weights, then the full optimization. I think it's a very similar story. It's just different input.
Yeah. I mean, I would be happy to take any suggestions on what else we can.
We got rid of the CRF.
Yeah. Okay, that's the end of the story. Cool. Okay, let's look at some results. I'm going to go all the way from the simple approach to the more complicated, but first the data set. These are optimization word problems. This was a challenge at NeurIPS in 2022, where we participated. The important bit is the source domain has problems from advertising, investment, and sales optimization problems. And the target domains have unseen problems in production, science, and transportation. So that's the kind of the generalization we are trying to achieve here. So that's the important part. okay, we're going to compare the classical with our classical feature engineered classical plus. We're going to compare XLM as our state-of-the-art, Roberta-based model. We're going to fine-tune that XLM RL plus and the hybrid that I mentioned to add one more feature into CRF. Okay, I'm going to look at the precision and recall and the micro F1 on each one of the entity classes. So how good are they predicting the constraint direction? How good are they predicting the limit? How good are they predicting the objective direction, and so on and so forth? So if you just take the classical, what exists in classical NLP, you get 81% micro F1. If you do the engineering that I showed you with automatas, gazetteer features, that maximizes very specific and so on, you can make that to 85. So there's some value you could get by just engineering your features. And the feature engineering is on the constraint direction and objective, and we actually see the improvements on those columns. So it does help where it is supposed to help. The classical seems okay, except the objective name and the variable, which is where the ambiguity problem is the hardest. So they're fine otherwise, but these two seems to be the hardest classes. If we just use the Roberta base or the Roberta large, you can get an 88, 89% right out of the box. So you could say, okay, why do you do feature engineering? Just get rid of it, throw the embeddings in there and get it. So which I think is quite nice. Correct, because this is difficult. So it does improve, and that's my comment. It doesn't improve in every case either. So the overall result seems okay, but again, it's not doing great in objective name. If you fine tune this thing, you can get some additional boost. To me, that's quite encouraging because our fine tuning is on very small data compared to what these things are trained on. So it's just a handful of optimization textbook that we can get our hands on. So this is quite nice. And as Fatma noted, it doesn't improve the precision and recall in every class. So, I can still see that the classical plus is doing quite well in the constraint direction because I spent quite some time with that regular automata. And I kind of know what these things might look like. So it doesn't mean, it's going to work in every class. If you just add that feature to your CRF, you get a bit more of a boost. So you can go up to almost 92 in this case. The nice thing is it gets the best performance on the most classes and the hardest classes, both the objective direction and objective. So you're getting a bit of the engineering that you can have and the robustness from your dense embeddings, and you're combining the two, and that seems to work okay. All right, so I'll skip where these things fail. They fail essentially because of some uncertainty. Do quite well compared to the competition, but I want to jump to the last part. How about ChatGPT? Why deal with this? Just give it to GPT and see what it does. You could just do that. You could give all these problems to GPT and say, okay, what are the entities here? Would give you something like that. If you read it carefully and see what it is doing, well, don't try to read that. I have a table that does it on a couple of hundred things. But you could, now, how do you exactly ask? Do you do it zero shot? Do you try to tell what is an objective a little bit? And so on and so forth. So there's different ways. Do you give some examples like we did in ChatOpt? Well, if you do that, if you just ask GPT-4, you're going to get like 54, 55. It's really bad. Because, classical NLP was 81. Okay. The nice thing is if you just give a bit of an example, you immediately jump to 83. So just seeing a few examples do help enormously. So from 50s, you go to that. So at this point, you could say, well, you didn't need all of these slides. You could have just give some examples to GPT and we'll be happy. Okay. But there's a bit of a caveat there. Like we are very careful in the examples we're giving to it. Like these are not just random arbitrary examples. We're crafting them. So it's not, I don't think my grandmother would get it right. So there's some, additional work that we're doing on top. But it's still beyond, 83 is still quite far from the 92 that we can get. But this is not really a very healthy comparison because I am doing a general purpose LLM with a very, supervised. I'll skip where ChatGPT fails, but if I just go ahead, so let's maybe circle back to where we started. the whole modeling assistance, if I just ask GPT-4, can you just model this problem? The compilation accuracy of the models that comes out of it, let's say 44%. If I run the NER for opt, the approach that I showed you, hybrid one, put the annotations that I find into the context of the GPT, then the compilation accuracy increases about 50%. So in some sense, these are not exclusive technologies. Like the more we understand the building blocks, we can bring in that value into our context and give more annotations and examples to the LLM, but in an automated way, so I don't have to craft the prompt either. So that's kind of like what we're doing at in recent work. I'm gonna maybe conclude here. Essentially, these are immediately relevant as a modeling assistant, but also I think these are very difficult NLP problems. So they're quite interesting to study from that aspect as well. There's also some computer interaction problems lying somewhere in here. Like, is the conversation the best way to engage with these systems? Or should it be like a GitHub Copilot? It's not very clear what that should look like. How do we actually get to a translation task? How do we go beyond the low data regime and get some data that would actually enable to do this end to end? How do we get there? There are some open problems, clearly interesting research area with increasing attention. And I'll conclude that part and we'll end on this slide just to give a sense of what we're doing these days at Fidelity. I already talked about NER for opt, but also we have some work happening on taking large LLVMs and being able to prune them, because we are interested in fast inference time and reduced to memory footprint. So we're looking at how to prune some large models. Responsible AI is a big part. We're looking at how we can get explainable models using some expressive Boolean formulas, and also looking at fairness and bias. Most critically for us is like the lack of ground truth in industry. Like, is not a ticket to not to evaluate your fairness, but all the academic work depends on it. So how do you relax those assumptions? Or things like access to individual protected attributes, which we don't have and are not legally allowed to ask either. But then how do you go and do these evaluations? A lot of work on contextual multi-arm bandits. We use them either for recommender systems and personalization or for optimization purposes. And lots of feature generation, whether it's from text, unstructured text, or sequential pattern mining, or tabular feature selection. And each of these works are accompanied with open source libraries. They're downloaded more than 1 million times in the community, so you could do just a pip install and get these things if any of them sounds interesting. So I'm gonna stop there and happy to take any questions you might have.